continue with our discussion on squeeze states. Do you have any questions? So let's recall, we are looking at one special state called the squeeze state. And within the squeeze states, we are looking at a single mode squeeze state. One mode, which means only one mode is excited, and that excitation is in a state which satisfies this condition. Where B is an operator which is defined by mu A plus mu A dagger, and the condition that mod mu square minus mod nu square is equal to 1. States which satisfies this equation are called squeeze states, because as we will see, these states have less noise than vacuum in some of the quadratures. So remember, we had shown that if you take the two quadratures, delta x delta y must be greater than or equal to 1 by 4. The minimum uncertainty states correspond to delta x delta y is equal to 1 by 4. And in vacuum, delta x and delta y are equal and equal to half. So if I have a state, I could have a state in which delta x or delta y is less than half. And that would correspond to what is called as quadrature squeeze states, which means in one of the quadratures, the noise is less than what is there in vacuum. And I'm going to show you that this state which satisfies this equation satisfies the condition of squeezing. Now, as I told you, to keep the analysis simple, we will assume mu, nu and beta to be real. But in general, mu and nu and beta are all complex numbers. So if mu and nu are real, I can actually write mu is equal to cos hyperbolic sigma and nu is equal to sine hyperbolic sigma. So that mu plus nu becomes equal to exponential sigma, and mu minus nu becomes exponential minus sigma. Now, please note that sigma can be positive or negative. If sigma is positive, mu plus nu is exponential plus sigma, and this is exponential minus sigma. If sigma is negative, then mu plus nu becomes less than mu minus nu. Okay, mu plus nu becomes exponential minus mod sigma, mu minus nu becomes exponential plus mod sigma if sigma is negative. So, as you will see, the quadrature which gets squeezed depends on the sign of sigma. So, we are looking at special kind of states called squeeze states, in which the squeeze states beta satisfy this equation b beta is equal to beta beta, where b is an operator defined in terms of the A and A dagger operators, the creation and annihilation operators. And you can actually, as I told you last time, you can substitute the commutation relations for A and A dagger and show that b dagger is equal to 1. So they are similar to A and A dagger operators. B dagger operators are similar to A dagger operators, and this equation is something like what we define for the coherent state. A alpha is equal to alpha alpha. So now we are defining another state with respect to B operators as B beta is equal to beta beta. So what I first calculate is the expectation value of electric field, and I want to calculate the variance in the electric field as a function of time and space. So last time we did this expectation value of E is equal to beta I E naught by 2 A exponential minus I chi minus A dagger exponential I chi beta, where let me recall chi is omega t minus b kz. I'm assuming propagation direction to be along z. And so I have to invert this equation. So actually I'm given b is equal to mu a plus mu a dagger. So b dagger is equal to mu a dagger plus mu a. This is for mu and nu to be real. And so we can invert these equations and write a is equal to mu b minus nu b dagger, and a dagger is equal to mu b dagger minus nu b. If mu and nu are complex, I need to keep here mu star, and similarly here mu star. So I have to be careful when I'm having complex values of mu and nu. But in this, right now we are assuming mu and nu are real, so that we can simply write a and a dagger. So I need to substitute this a and a dagger here and calculate the expectation value of the electric field, which we did last class. And what we obtained was E expectation value is equal to E naught times mu minus nu into beta sine omega t minus kz. Also note that if I put nu is equal to 0, what will the state beta correspond to? It becomes a coherent state, because if nu is 0, B becomes A operator. So B beta is equal to beta beta becomes A beta is equal to beta beta. So effectively the state becomes a coherent state if nu is equal to 0. So here if you put nu is equal to 0, you will get epsilon 0, mu must be equal to 1 because of this condition. If you put nu is equal to 0, mu is 1, and you get E0 beta sine omega t minus kz, which is exactly the same as what we had got for the squeeze state, the coherent state. Now I need to calculate E square expectation value, and we started doing it last time. This is beta into minus E naught square by 4 A exponential minus I chi minus A dagger exponential I chi whole square beta. So when you expand this square here, you will get minus E naught square by 4 A square exponential minus 2 I chi plus A dagger square exponential 2 I chi minus A dagger minus A dagger A. So I need things like expectation value of A square, expectation value of A square, expectation value of A dagger square, expectation value of A dagger, and expectation value of A dagger A. So I have to substitute for A in terms of B, which I have got here. I have to replace A by B and B dagger and use the condition that B beta is equal to beta beta. And what is the corresponding conjugate expression for this? Beta B dagger is actually beta star beta. If I assume beta to be real, this is beta beta. Please note, B dagger beta is not equal to beta star beta. Okay, B dagger, if it operates on ket beta, does not give me beta star. Okay, it is B dagger operating on bra beta, which gives me beta star beta or beta times beta if beta is real. So I need to use this equation, and after substituting the expression for A and A dagger, this is a bit of algebra, very simple algebra, and I will just give you the expressions. Please verify yourself. So this is beta square into mu minus nu whole square minus mu nu beta A dagger square beta is equal to beta square mu minus nu whole square minus mu nu. Beta a dagger beta is equal to beta square into mu minus nu whole square plus nu square plus 1, and beta a dagger a beta will be beta square into mu minus nu whole square plus nu square. Because a dagger is equal to a dagger a plus 1, there is a difference of 1 between expectation value of a dagger and a dagger a. So I need to substitute the expressions for a and a dagger in terms of b and b dagger. Use the condition that b beta is equal to beta beta, and similarly for the b dagger operator, and a little bit of algebra will give you these expressions for a square expectation value, a dagger square expectation value, and expectation value of a dagger and a dagger a. So I now substitute all this into this equation, and here is what I will get. Expectation value of E square is equal to E naught square by 4 mu square plus nu square plus 2 mu nu cos 2 times omega t minus kz. If you calculate all the expectation values substituted into this cos 2 times omega t minus kz is coming from these terms. See, a square expectation value and a dagger square expectation value are equal, so essentially you will get a cos 2 chi coming from here. And I have the expectation value of E, which I have derived earlier, is equal to E naught mu minus nu into beta sine omega t minus kz. For the coherent state, I can obtain by putting nu is equal to 0 and mu is equal to 1. And if you put nu is equal to 0, look here, this expression disappears and the expectation value of E square becomes independent of time for a coherent state, which is what we had seen.
There is no beta in the expectation value of
E square? No, no. So if you put nu is equal to 0, you get the coherent state, and the expectation value of E square in the coherent state is independent of time. Here, it's a function of time. So let me try to plot the electric field variation. Okay, so let me plot at z is equal to 0. I choose a point at z is equal to 0 and plot E as a function of time, expectation value of E as a function of time, and around that value, expectation value of E square. So what is delta E square? The variance in E is given by E square expectation value minus E expectation value square. Sorry, this is I'm sorry. I'm sorry. This is delta E square. I'm sorry. Let me write the expression for E square. 1 second. So E square expectation value. Please correct this. E naught square by 4 beta square mu minus nu whole square sine square omega t minus kz. You're right, there is a beta here. Plus 2 mu nu cos 2 times omega t minus kz plus 2 nu square plus 1. Please correct this. This is the expectation value of E square. and it depends on beta. So to calculate the variance, I need to do E square expectation value minus E expectation value square. So the first term here is E naught square beta square mu minus nu whole square sine square omega t minus kz is nothing but E expectation value square. E naught square beta square mu minus nu whole square sine square omega t minus kz is nothing but expectation value of E whole square. So that cancels off and I am left with E naught square by 4. Now 2 nu square plus 1 is mu square minus nu square. So 2 nu square plus 1 is mu square plus nu square. So mu square plus nu square plus 2 mu nu cos 2 times omega t minus kz. So the variance in electric field, it depends on time and varies in this fashion. So let me try to plot how the electric field will look like if I were to measure as a function of time. So and I position myself at z is equal to 0. Okay, so I have expectation value of E is equal to E naught mu minus nu beta sine omega t, and delta E square is equal to E naught square by 4 mu square plus nu square plus 2 mu nu cos 2 omega t. So depending on the values of mu, nu and beta, the expectation value varies sinusoidally. And let me plot a dashed line here. This is the expectation value. It goes like this. At the frequency omega. Which means on an average, if you were to measure the ensemble average of the electric field, you will get this dependence. It's a sinusoidal dependence, but now if you look at this equation here, the variance in the electric field depends on time. So at t is equal to 0, this becomes mu square plus nu square plus 2 mu nu, which is mu plus nu whole square, which if nu is positive, what is the value? So at t is equal to 0 and then pi by omega, 2 pi by omega, etc. Delta E square becomes E naught square by 4 into mu plus nu whole square, which is exponential 2 sigma. Assuming mu is equal to cos hyperbolic sigma and nu is equal to sine hyperbolic sigma. And at t is equal to pi by 2 omega, 3 pi by 2 omega, etc., delta E square becomes E naught square by 4 exponential minus 2 sigma. What is delta E square for the coherent state? E naught square by 4. So nu is equal to 0, mu is equal to 1. So at certain times, the variance in the electric field is more than the coherent state, and at other intervals of time, it's less than the coherent state. So if I were to plot this, I will have, for example, this will be the variance here at t is equal to 0, t is equal to pi by omega, t is equal to pi by 2 omega, etc. Here the variance is much smaller. So which means if I draw the region of electric field which you will measure, it will look like this. the variance depends on time. At certain times, the variance here is less than what you will achieve in coherent state or in vacuum. Please remember, the variance of the electric field in the coherent state or is equal to that in vacuum. So here the variance is less than in vacuum, but correspondingly there are other times where it is much bigger than vacuum. You cannot have variance at all times less than vacuum. This is related to delta x delta y greater than or equal to 1 by 4. So what is actually happening is, at these intervals of time you are having larger variance than vacuum. At other intervals of time you are having less variance than vacuum. So what is happening is, the point of intersection with the axis is ill-defined. The phase is ill-defined, but the amplitude is more precisely defined than in a coherent state. If I were to measure the electric fields at this intervals of time, I will get an electric field value which is better than or less noisy than I would have got if I had vacuum or if I had coherent state.
But that again depends on the time instant.
Yeah, so I need to do a measurement which is called homodyning, which will measure one of the quadratures. When I discuss the quadrature, it will become clearer. I must measure one of the quadratures of the electric field which has less noise than the other quadrature. So what is actually happening is, the amplitude of the electric field is more precisely defined than phase here, much more precisely defined. If nu is equal to 0, you get the coherent state and the variance is independent of time. It's an equal thickness curve which I plotted last time. So what I'm saying here is, this is characteristic of a squeeze state. In fact, if nu was negative, what will I get? Sorry, if sigma is negative, nu is negative, in that case I would have got another state which is different. I would have got a state like this. If sigma is negative, then at these intervals of time the noise is less than vacuum. At these intervals of time the noise is more than vacuum. So I would have got, suppose this is my expectation value. Here the noise is less, here the noise is more. So I would have got like this. The phase is more precisely defined here at the cost of a greater noise or uncertainty in the amplitude of the electric field. So depending on the sign of sigma, I can have either squeezing or reduced noise in the amplitude quadrature here or the phase quadrature here. We will now calculate the noise in x and y quadratures, and that will give us a better picture, and we can then draw the Phasor diagram and see how the Phasor diagram looks for a squeeze state. Is this clear? So these are some special states. The problem is, how do I produce these states? We will come to it later. But these are some special states in which I can have reduced noise in one at the cost of increased noise in the other. Okay, now let me calculate. So for the Phasor diagram, I need to calculate expectation values of x, y, and then variance in x and variance in y. So I need to calculate expectation value of x, which, remember, this is defined as beta a plus a dagger by 2 beta. Now I'll just do a calculation for 1 or 2, and then I'll leave the remaining to you. So this is beta, half of beta. So this is mu b minus nu b dagger plus mu b dagger minus nu b beta. Half of Now, B on beta is beta beta, and beta into beta is 1 normalized, so I get mu beta. The second term, B dagger on beta bra is beta beta, because beta is real, so I will get minus nu beta. Again, this B dagger acting on beta bra gives me beta into beta bra. Beta bra into beta ket is 1, so I get plus mu beta and then minus nu beta. I am assuming beta to be real, otherwise I would have got beta dagger operating on bra beta would have given me beta star into beta bra. So this is equal to nu minus nu beta. X square expectation value 1 by 4 beta a plus a dagger square beta, which is 1 by 4 beta a square beta plus beta a dagger square beta plus beta a dagger beta plus beta a dagger a beta. It's just algebra, a little sometimes becomes tedious to simplify, to calculate, etc. But let me give you the expression for this. Again, you need to calculate, substitute the values of A in terms of B and beta dagger, B and B dagger, and use the equations, and what you get is the following: beta square into mu minus nu whole square plus 1 by 4 actually the second term is
Mu minus nu.
yeah, so this is beta square into mu minus nu whole square plus this is 1 by 4 of can we estimate expectation value of y? Yeah? 0. Yes, expectation value of y is 1 by 2i beta a minus a dagger beta, which is 0. So I leave this to you to show that expectation value of y square is equal to 1 by 4 So variance in x is x square average minus x average square, which is equal to, now this first term beta square mu minus nu whole square is exactly equal to x average square. That cancels off and I am left with 1 by 4 mu minus nu whole square, which is mu minus nu is exponential minus sigma, and delta y square is y square average minus y average square, which is equal to 1 by 4 mu plus nu whole square, because y expectation value is 0 and I get exponential 2 sigma by 4. And delta x delta y is equal to, it's again a minimum uncertainty state. It's a minimum uncertainty state because the product of the uncertainty in x and y is 1 by 4. But delta x and delta y are not equal. And if sigma is positive, remember in coherent state delta x square was 1 by 4. So if sigma is positive, delta x square is less than in coherent state, while delta y square is correspondingly more than the coherent state. Similarly, for sigma negative, delta x square is more than coherent state and delta y square is less than for coherent state. So I can actually draw a Phasor diagram now knowing these numbers, expectation value of x, expectation value of y, delta x square and delta y square, and here is the Phasor diagram. So where will the spot appear? Expectation value of x, expectation value of y. At some point where? On the x-axis, because expectation value of y is 0. So it will be somewhere here, whose value is mu minus nu into beta. Okay, this point is actually, which is exponential minus sigma beta. Now, how will I draw the area for corresponding to delta x and delta y? For the coherent state, remember, delta x is equal to delta y and you get a circle. Here, if sigma is positive, delta x is less than delta y, delta x is less than for coherent state, and delta y is more than for coherent state. So if the coherent state was something like this will correspond to figure like this. Delta x, I'm sorry, this is for sigma less than 0. Let me draw for sigma greater than 0. The circle in the case of coherent state, which corresponds to equal uncertainties in both the quadratures, gets squeezed into an ellipse. And in this case, the squeezing is in one direction. In this case, the squeezing is in the opposite direction. This particular state here has less noise in the x quadrature than the coherent state, but it has more noise in the y quadrature. This state has less noise than the coherent state in the y quadrature, while it has increased noise in the x quadrature. So these are called squeeze states, quadrature squeeze states, because the squeezing is in one of the quadratures, and what it implies is that if you were to, please remember I had told you that this distance is something like the amplitude of the electric field. So there is less noise, as you can see here, for sigma greater than 0, as you can see from this plot that we had here, that there is less noise. For sigma positive, as you can see here, there is less noise in the amplitude and more noise in the phase. For sigma less than 0, there is more noise in the amplitude and less noise in the phase. Here, this angle, as I was telling you, is something like the angle, the phase. The phase, uncertainty in phase, is something related to this. This particular state has more uncertainty in phase than the coherent state, but it has less uncertainty in the amplitude than the coherent state. Less fluctuation in the electric field, amplitude. Here, the fluctuations are in the other quadratures. Yes, Mohit.
Sir, by seeing those graphs that you have drawn,
Yeah.
The amplitude and phase graphs, how can you say that the peak corresponds to the amplitude and the points where it intersects?
No, I'm just, by that I mean the amplitude of the electric field, which is proportional to something like the number of photons in the state, has less uncertainty. Because the amplitude is more certain here. I know the amplitude more precisely than I knew for a coherent state. If I were to measure precisely the electric field at these instants of time, I will get a value of electric field more precise than what I would have got if I had a coherent state. So this state has less noise in amplitude than a coherent state. And the coherent state is the one that is produced by a laser. So this particular state has less noise in amplitude quadrature or phase quadrature depending on the sign of sigma that I choose. Later I will tell you how to measure one of the quadratures. How to measure the quadrature corresponding to x or y in an actual experiment so that I can actually use this less noise, the presence of less noise to my increasing my detection sensitivity. And these are the type of squeeze states that are used for gravitational wave detection, because these states can have less noise than what you can get with simply laser beams. You can reduce the noise. Now there is something interesting that I want to check, and that is, let me calculate the average number of photons in the state. What do I have to calculate? Expectation value of n, which is beta a dagger a beta. So this is beta. Now a dagger in a I must substitute. We have calculated a dagger a. Expectation value, yeah, we have calculated. So what is the value of this? Beta square okay, now yeah, okay, so this is for the squeeze state. What will I get for the coherent state? Assuming that a beta becomes equal to beta beta. Okay, so I just put alpha is equal to beta in this case. So what do I get? Which is mod alpha square we got, remember. Expectation value of n was mod alpha square. Average number of photons in the state was mod alpha square. I am just replacing alpha by beta and assuming beta to be real. So I just get, instead of mod alpha square, which we did, I just get beta square. Now, there is an interesting state called vacuum state. What is a vacuum state? Vacuum in the sense of radiation. A state in which none of the modes are excited. So if I look at the single mode, if I am in the vacuum state of the single mode, what is the equation satisfied by the vacuum state? A normal vacuum state. What is the equation? What is the state by which is the limit into which I reach as I keep on removing photon after photon from a Fock state? A on 0 is equal to 0. This is called the vacuum state. Because if I start with any nket state and I keep on applying a operator, I keep on destroying one by one photon, and finally I will reach a state which is the lowest energy state, which is called the vacuum state, where this corresponds to n is equal to 0. So what is the expectation value of n in the state? 0, a dagger a, 0. Okay, there are expectation value 0. Now we define what is called as a squeezed vacuum state. similar to this equation by saying B0, let me put S here just to tell you it's a state of the lowest eigenvalue. Beta is equal to 0 eigenvalue. Just like A0 is equal to 0, I call as a vacuum state, I am calling B0 is equal to 0 as the squeezed vacuum state. And what is the expectation value of n in the squeezed vacuum state? Is equal to, because I can use this equation which I just now wrote, beta is equal to 0, and so I get nu square, which is sine hyperbolic square. So a squeezed vacuum state has photons in it. Expectation value of measuring photon number in that squeezed state is finite, it's not 0, because I get sine hyperbolic square sigma. It's called vacuum state because it's the lowest state corresponding to the B operator, but it's called a squeezed vacuum state because that's a state in which B0 is equal to 0. And so the squeezed vacuum state actually has photons in it, and if I were to draw the vacuum and the squeezed vacuum state in a phasor diagram, how will I draw? So please note, what is delta n square? We had expression for, no, we didn't calculate delta n square. Okay, let me calculate delta. What is delta x square for the squeezed vacuum state? We had an expression for delta x square. I put beta is equal to 0. It's actually independent of beta. Exponential minus 2 sigma by 4, and delta y square is equal to exponential 2 sigma by 4. And what will be the delta x delta y for a vacuum, for a coherent state, for a coherent vacuum state? 1 by 4 and 1 by 4. Okay. So if I draw the phasor diagram, a coherent vacuum state will look like this. Expectation value of x is 0, expectation value of y is 0, delta x square is 1 by 4, delta y square is 1 by 4. This one, a squeezed vacuum state with sigma positive, will be like this. Expectation value of x is again 0, expectation value of y will be again 0. If you go back and look at the expectation values of x and y for the squeezed state, for the squeezed vacuum state, if you put beta is equal to 0, then expectation value of x becomes 0, expectation value of y is 0, delta x square, delta y square are given like this. So this is one squeezed state, and the other one will correspond to squeezing in the other direction. So that's interesting because even when I have nothing, I have this noise. If it was a coherent vacuum state, which means I come to a state which is the 0 state corresponding to n is equal to 0 number of photons. In that mode, there are no photons. There is a fluctuation in the x quadrature, there is a fluctuation in the y quadrature. They are equal. Delta x is equal to delta y, which means if I were to measure the electric field x quadrature or electric field y quadrature, I will find noise. If I could prepare a state which I call as the squeezed vacuum state in which B0 is equal to 0, then with sigma positive, for example, I will have less noise than I would have got even when there was nothing. This is a state in which there are a finite number of photons. Please remember now, this is not a vacuum. There are now some photons in the state because expectation value of n is not 0. It is sine hyperbolic square sigma. So there are photons in the state now, but what is happening is the uncertainty in the x quadrature is less than what you would have got had you had no photons. This is called squeezed vacuum. In this quadrature, you can squeeze the vacuum in the y quadrature by taking a sigma which is negative. Of course, you pay a price of increasing the noise in the other quadrature. So you have to do a measurement which is phase sensitive, because you need to measure the x quadrature or the y quadrature. You need to do a phase sensitive measurement, and that is typical in homotonic. So I will tell this, bring up this concept of homotonic a little later, but it's very interesting to note that if I could choose states for which satisfy the condition of the squeeze state condition, then I can go to a state which is the lowest state of the B operator, in which case I have less noise than vacuum in one of the quadrature at the expense of increased noise in the other quadrature. Yes, Sharvil.
Physically, the x and y operators, what do they represent? So if I'm doing a physical experiment,
Yeah, remember the electric field has x sine omega t minus kz minus y cos omega t minus kz. So the sine term, sine and cosine are pi by 2 out of phase. So they are the two quadratures. If I could measure the amplitude corresponding to the sine term, I will get the expectation value of x. If I could measure the amplitude corresponding to the y term, the cosine term, I would have got the expectation value of the y operator. So I need to be phase sensitive now. I need to be sensitive to only pick up the sine part of the electric field to get expectation value of x. And that is possible because phase sensitive means I must have another reference phase with respect to which I match and calculate and measure, and that's what is homotonic essentially. So homotonic is a very general principle which is used in engineering for signal detection and signal processing, but here we will use optical homotonic. I'll explain to you how it can lead to very interesting situations. And let me tell you, this decreased noise in vacuum is an experimentally measured quantity. And a parametric down conversion process is a process which can lead me to these kinds of squeeze states. Okay, so yeah, do you have any questions on this? So these squeeze states are very interesting because you can have reduced noise in one quadrature at the expense of the other. Here we have assumed mu, nu and beta to be real, but in general, please note that I could have a state which will be squeezed may look like this. So a coherent state may be like this, a squeeze state squeezed in some arbitrary direction, right? Here I am showing either horizontal or vertical ellipses, but in general I could have a expectation value of x and expectation value of y which are non-zero, both non-zero, and the squeezing is not in the x and y quadrature but in another pair of quadratures. So this squeezing is taking place from a circle to an ellipse in some orientation, and that's a more general squeeze state. This kind of states you will obtain if you were to choose complex values of mu, nu and beta. Okay, I think we'll stop here. So what I want to do next time is maybe go on to what we call as multimode states. Because till now we are talking of states in which only one mode is excited. Light is present in only one mode, one frequency, one propagation direction, one polarization state. I want to extend this into a state where I can have at least two modes, which means same direction of propagation but two different frequencies, or the same frequency but two different propagation directions. And that is where I will start to see interference effects, because with single frequency I don't see any interference. To interfere, I must have either two frequencies or two waves going in two different directions, and that will be generated at least by a state which contains two modes. Okay, so we'll start to look at two mode states, and then I will try to calculate what do we actually measure when we do an interference experiment, and this mathematical structure will explain what we had started with in the beginning, that in a beam splitter with single photons coming in, only one of the detectors clicks. But if I make a Mach-Zehnder interferometer, there is interference taking place. Both these experiments will be explained by this mathematical structure. Okay.